All right, in this video, we're talking about the theory, okay? So with the theory, let's just go ahead and write this out. And I need to write. So we will start off with two kinematic equations, and we're going to reduce them based on some considerations. So the kinematic equations are as follows. Do this again. It's going to be the displacement in the x direction equals to the initial velocity times cosine of theta, which is the velocity in the x direction. The product of those two is the velocity in the x direction. And then we're going to multiply that times time. And this is going to be added to 1/2 the constant acceleration times time squared. So that's our first equation. The second one looks like so. And this is going to be 1/2 times the acceleration in the y direction times t squared. So for the first equation, we're going to make the assumption that there's no acceleration in the x direction. So what do I mean by that? We're going to fire a ball out like so. And the velocity that we want to know is this velocity. When the ball is in the chamber at this location, what is its velocity? This is the question that we're trying to answer, okay? So this ball is going to be launched. It's going to land somewhere on some surface, okay? And what we're saying is from this point to this point, there will be no acceleration in the x direction. So let's be very clear on what these points are. This is your first point. And this is your second point. So we're saying that there's no acceleration in the x direction, which has a direct consequence on the x equation, because now this entire piece goes away. So I can rewrite this as xf minus x initial, displacement in the x direction, is equal to the initial velocity times cosine of the angle of launch times t. That is a very, very nice reduction there. Okay.